Okay, thank you very much. And I didn't know that I should speak English, and I prepared the Japanese talk. So today I would like to discuss computational nanomaterial design, and very different from the previous talk. And in Osaka University, we developed a computational nanomaterial design system. In this case, using the quantum simulation, we can predict a lot of developed a lot of software. This is open for the public. Then using the quantum simulation, we can analyze the physical mechanism. Then once you know the physical mechanism, integrate the mechanism, you can predict a lot of new functional materials. And then using the quantum simulation, you can verify the functionality. Then you can just combine the experimental verification. We can design and also realize a lot of new material. This is we call the computational nanomaterial design. But most of the case, people use local density approximation. This does not work sometimes. Sometimes it's a disaster. Then we developed self-interaction corrected LDA. This works very well. Today I will discuss a little bit about cobalt doped zinc oxide. And also, we need very large-scale calculation. We call it order n. And then, for example, if we want to discuss this kind of Schottky barrier, we need 10,000 of the layers. And also, especially important point, the quasi-particle spectrum, like a band gap, LDA cannot predict very well. So we developed a quasi-particle cell-consistent GW method. For example, if you looked at the spin wave excitation, LDA is very poor compared to the experiment. And you can, but using a QSGW, we can predict very well about this one. And also, in order to discuss a large scale of something like a nanoscale size separation, we should develop this is called we call the multi-scale simulation in order to discuss self-organize this nanostructure. And using this kind of software, we can design a lot of things. Today, I would like to discuss a spinodal nanodecomposition as a new class of bottom-up nanotechnology. For example, this is a very prototype. You can dope the chromium in zinc telluride. This chromium and zinc is just like oil and water. You cannot mix. Then you can calculate the mixing energy at a low temperature. This is positive and very strong convexity means that you cannot mix because of that it costs very expensive. Then at finite temperature, you can calculate the free energy from the first principle. This is a mixing entropy. Then you can still use to see that this kind of convexity and the second derivative of the free energy is negative. In this region, we call it the spinodal region. So in this region, if you dope the very high concentration, using a little bit fluctuation of the concentration, you can see low concentration region becomes low, high concentration becomes higher. Then, because this is lower the free energy. So in this region, if second derivative of the free energy is negative, this region we call the spinodal region. In this case, you can dope homogeneously zinc and chromium when they completely break the symmetry and the low concentration becomes lower and the high concentration region becomes higher. Just like capitalism, rich people become very rich and the poor people become poor. In this case, the impurity diffuses from low concentration region to the high concentration. We call it uphill diffusion. So, using this kind of nanoscale, high concentration, low concentration region, you can need a very low temperature, then you can make a very sharp interface like this. Nanoscale size spinodal wavelengths. Then in this case, we call the spinodal nanodecomposition. Then if you go to a little bit high temperature, if you have double minimum, you have a common tangent. At this point, we call the binodal line. In this case, with nucleation, you can have a phase separation. But in spinodal decomposition, without any nucleation, you can make a high concentration and low concentration region in nanoscale size. So this is the most important point. So of course, you can control the dimensionality of the crystal growth. You have a substrate in here. Then you put on the A and B atom. This is for example, zinc and chromium in zinc telluride. Then homogeneous doping. Then after you can start a diffusion here. Then you can see very small clustering like this. Then you can quench the crystal growth. You can grow next layer. Then during the diffusion, this atom stays just on the top because of this is just oil and water. Then if you grow layer by layer crystal growth, in this case, you can grow inside the A matrix, you can grow the B high concentration region. matrix is the same, like a zinc telluride. Here you have a zinc telluride, and this is a chromium high concentration region. Then you can grow this kind of nanowire using the cell organization, very large scale of size. Because we need, for example, in order to design the photovoltaic solar cell, we need 3 or 4 hectares of the size, very large one. Then we can use this kind of spinodal nano decomposition, just controlling. This is a simulation. We can calculate the effective chemical pair interaction between the atoms. Then using the Monte Carlo simulation, you can grow the crystal growth. This is a completely disordered system. Low concentration region, 3-dimensional growth, you can see this kind of small clustering. Then if you grow layer by layer, you can see this kind of 1-dimensional nanowire. This is so-called comb phase. Seeding is possible. You can grow this place like this, and shape control is also possible. During the crystal growth, you can just reduce the vapor pressure. You can make a thinner nanowire. Then you can increase, you can recover like this. So all of the shape control is possible. This is completely nanoscale size. You can just paint and spray, then just bake. You can grow this kind of system. Okay, so experimentally, for example, in the case of germanium manganese case, this is just like oil and water. You can top view, and at the perpendicular plane, you can see this kind of nanowire like this. And this is aluminum doped gallium arsenide. You can see so beautiful nanowire here. This is a top view. Then diameter is 2 nanometer. Average distance is only 7 nanometer or something like this. Then now this kind of things are possible. But if you go to the very high concentration, like a 30% case, this is a completely disordered phase. Then if you go to the spinodal decomposition, you can atoms start gathering like this. Then you can make, in the case of high concentration, you can make this kind of a complete network in whole your crystal. If exchange interaction is very short range, for example, ferromagnetic semiconductors, in this case, TC is very low because you have a very small power correction path. But if you can organize spinodal decomposition, you have a completely power correction path on whole your crystal. You can realize a very high TC. I will discuss later. And we are using this kind of spinodal decomposition in order to make a high efficiency photovoltaic solar cell. You can mix the 2 kinds of semiconductor. This is a type 1. This part is a type 2, type 1 band gap alignment. So electron running this way, holes running this way. So you can completely separate the electron hole. And also using this kind of, nanowire, you can use some discrete energy levels in order to realize multi-exciton formation using the inverse Auger effect. So that's about a different story of the opera. Today, I would like to discuss semiconductor spintronics. Okay. Then this is a very important thing. Then using this kind of new class of bottom-up nanotechnology, we call spinodal nanotechnology, you can make a very small nanoparticle using the spinodal nano decomposition. Then you can design the catalytic system. In catalytic system, we need nanoscale size. If size becomes larger, completely lost the catalytic functionality. And we have many kind of applications I'm working now. But today, I would like to discuss the material design of the semiconductor spintronics and the realization of high TC DMS. For example, this is the case for the manganese doped gallium arsenide, 5% doping. This is LDA. This is cell interaction corrected LDA. You can see that very large exchange splitting compared with the LDA. Photoemission experiment predicts the manganese 3D is around here. Then large exchange splitting, top of the valence band is push up. And this is pull down. Then in this case, ferromagnetic mechanism, we call the Zener's PD exchange mechanism. Then itinerant P holes stabilize the ferromagnetism. You can calculate the exchange interaction as a function of the distance using the atomic force theorem. This is very long-range exchange interaction because of the P carrier holes. Then we can mapping on this kind of Ising model, Heisenberg model. Then after that, you can calculate the TC using the Monte Carlo simulation. This is developed 90s by Binder and also Landau. Then in this case, just the input is atomic number. You can calculate the exchange interaction as a function of the distance, and mapping on the Heisenberg model, you can calculate you can predict the TC very, very accurately. So this is about the case of the manganese doped gallium arsenide. In this case, arsenic P level is very shallow because of the orthogonalization. But if you look at the manganese doped gallium nitride, this is completely different. Nitrogen is a 2p, second period. We have no 1p. 2p level is very deep. Because of that, manganese 3D band is pushed up into the band gap. Like this, and very deep impurity band. This is partially occupied. Then this stabilizes ferromagnetism. This cause Chena proposed two kind of mechanism, and 9050 is assumption like this. But this mechanism and PD exchange mechanism cover whole of the world. And Chena's double exchange mechanism predicts in this case, manganese doped gallium nitride, Chena's double exchange dominated because impurity band is mostly constructed as a manganese 3D electron. Then in this case, 3D electron is hopping in your crystal. Then because of that, the deep impurity band, you can see exchange interactions very, very strong, but very short range. Then because of that low concentration region, you cannot get a perforation pass. Then TC becomes very, very low. We need very high concentration in order to make a ferromagnetic pass in a crystal. So mechanism is different. And then this is, for example, case of the cobalt-doped zinc oxide. LD is extremely wrong compared with the photon emission experiment and the core levels and 3D state and two-hole bound state. This is a self-interaction corrected LDA. You can see that this is a two-hole bound state and the cobalt 3D and E and T is completely separate. This is transparent for our visible light. And then in this case, antiferromagnetic super exchange dominate. Then if you have an electron doping, then you can stabilize the ferromagnet in this case. This is a photon emission experimental data. And now you can calculate the exchange interaction as a function of the distance, then mapping on the Heisenberg model using the Monte Carlo simulation. You can calculate TC as a function of the temporal concentration. Then blue one is the experiment, Monte Carlo simulation. Red one is experiment. You can see very reasonable agreement compared with the theoretical prediction and experiment. In this case, for example, prediction first, then people did experiment like this. Then now we have developed, if system is completely homogeneous, just using the atomic number, you can calculate the TC and also concentration dependence, something like this. Then now our question is how to increase the TC in the case of diluted magnetic semiconductor. One point is we should increase the solubility, because if you look at most of the case, with increasing the concentration, TC is going to up. In the case of chromium-doped zinc telluride, we have just room temperature ferromagnetism, but we need much more high TC. So in this case, we should increase the concentration much more. Then in this case, we propose the co-doping method. Because of the, if solubility is very small, always you can find the self-compensation. This is a Mother Nature's co-doping. Or if you dope a manganese in gallium arsenide, manganese doped gallium arsenide automatically creates the manganese interstitial donor. Then that is a double donor, compensates the manganese substitutional single acceptor. Then we can introduce artificially co-doping. Then after the crystal growth, you can remove out the co-dopant. That's Yamamoto-san and myself developed many years ago. This is so-called co-doping method. So in this case, most of the important point is after the crystal growth, we should remove out the co-dopant. That's a lithium and copper interstitial donor. This is very nice. This is a gallium arsenide diffusion constant versus inverse temperature. You can see copper and lithium diffuse very, very fast in the case of gallium arsenide compared with another defect. Then you can choose the lithium, beryllium, sodium, copper, silver, interstitial, because the silver is also very fast diffuser. This is a calculated mixing energy as a function of the manganese concentration. You can see that with increasing the manganese concentration without doping, you can see the mixing energy is positive. It means it costs very expensive and solubility is very low. But if you dope a little bit lithium interstitial donor with manganese acceptor, you have a negative one. Then 3 or 4%, you can introduce 30 or 40% of manganese at the substitutional site. All of the case. Then, but the problem is after that, we should remove out. Then, in order how to remove out, and then we should calculate the potential surface, and then using the dynamical Monte Carlo simulation, we can simulate the annealing out depth profile like this. In the case of lithium, for example, this is the case. This is a manganese interstitial double donor. This is in the case of cell compensation. For example, 444 Kelvin, if you dope the 15% of the, for example, manganese doping, you can remove out the lithium only 0.014 or micrometer. But if you choose the lithium, you can easily remove out the lithium very much. Then this works much more well. But in our calculation, I think kappa is our best candidate because we, for example, this is a kappa intershell in gallium arsenide. This is a migration barrier. This is 0.18 electron volt. This is extremely small. Then, of course, you have a manganese at the substitutional site. Manganese substitutional site at the substitutional site, the single acceptor, we can compensate the kappa, and we have a binding energy. So in order to remove out, we should calculate the dissociation energy. Like this is 0.41 electron volt. This is all case. Manganese intershell double donor, lithium intershell single donor, kappa intershell single donor. In this case, diffusion barrier becomes smaller and smaller from manganese to kappa, and dissociation energy becomes very small. Means kappa intershell impurity can bind manganese substitutional site very, very small compared with self-compensation. So using the kappa and lithium is a very good candidate for the codopant in order to increase the manganese solubility, and after low temperature annealing, you can remove out. That's a process. So in this case, 30% is very easy. If you use the kappa intershell donor codoping, and TC is going to cross to the something like 450 Kelvin like this. Then if you look at the migration barrier of the kappa lithium manganese, kappa is very, very low. Because of the kappa plus is D10, first excited state is the D9S1. This is very, very close. Based upon the second order perturbation, as a function of the displacement, this barrier becomes smaller and smaller. This is called the pseudo or Yantera interaction. This comes from the originally charge fluctuation. And then compared to the lithium, kappa is very heavy compared to the lithium, but still you see very, very low migration barrier. In silicon, this is famous. When people change the wiring from aluminum to kappa, kappa migrate very fast. So we need kappa gathering and in order to fix kappa intershell, because of the kappa diffuse very, very fast in the case of semiconductor. That's the reason. So another possibility is design of the high solubility in the ferromagnetic in 4-6 semiconductor. This is very, very nice because of the solubility is extremely high. If you use a molecular beam epitaxy, you can dope 96 or 80% doping in the case if you choose the 4-6 semiconductors. And that case is, for example, germanium 12. We have a lot of material because this is a 4-6, but actually this is a T6 because of the valence electron, the S2P2. Then in this case, chalcogen atom, this is S2P4. Then this receives the 2 electron. Then this metallic ion becomes 2 plus. This becomes 2 minus. Then this is something like a 2-6 material. Then germanium S level and selenium, for example, P level is very close. This repel very strongly each other. Then top of the valence band becomes anti-bonding state due to the very strong repulsion. Because of that, P-type doping is very easy. You can just introduce a germanium vacancy. The solubility of the germanium vacancy is very high. You can introduce a 30 or 40% very, very easily in this material. Then, because of that, band gap is very small, and then we have tried this kind of many kind of doping in these materials. Then, if you look at the phase diagram, germanium 12, for example, manganese 12, if you discuss manganese doping in germanium 12, this is a concentration. You can see very, very homogeneous doping region, even 90% or something like this. And Fukuma-san, he did molecular beam epitaxy crystal growth, and using a non-equilibrium growth, we can dope 96%. This is possible. And Of course, in thermal equilibrium, we have a lot of phases around it, like this. Then this is our initial calculation. You can see that, for example, this is 30% of manganese doped gallium nitride. You see large exchange splitting. This is because of manganese 2 plus is substituted, germanium 2 plus is substituted manganese. So we have no carrier here. In this case, magnetic interaction is antiferromagnetic super exchange interaction. We can compare this is a photon emission experiment, this, and very good agreement, and also this one is something like this. Then similar to the electronic structure is something like similar to the manganese doped gallium arsenide. But most of the important point compared with the gallium manganese arsenide, we can dope the very high concentration of manganese. And also, doping is very easy, especially P-type doping. Crystal is very happy because of the top of the valence band is anti-bonding state. If you introduce a hold, you have an empty anti-bonding state. Then crystal becomes much more stable. Because of that, formation energy is sometimes negative. Then Fukuma-san did this kind of experiment, and this TC versus hole concentration. They don't control the carrier density doping, and TC is going to up to 190 Kelvin. This is realized. In this case, carrier density is 10 to the 21st or something like this. But we need some systematic study, and also how large TC can be reached based upon the initial calculation. We can predict if the system is homogeneous, we can predict the Curie temperature very, very correctly. This is a case for the calculated result. You can see this is a manganese 10% doping. Then if you make a hole doping here, then this is like a Zenard physics exchange mechanism. You have this very large exchange splitting and the holes are around fair, destabilize the ferromagnetism. So if germanium vacancy is 0, in this case, antiferromagnetic super exchange, this exchange interaction versus distance, negative in the antiferromagnetic super exchange interaction, then this is Tn. Then upon hole doping, 5%, 10%, 10%. TC is gradually increased like this. This is a manganese concentration like this. Then in this material, we can dope very high concentrations of the manganese, and we can reach the very high TC very easily. But the best candidate is chromium. Chromium case, you can see this is chromium 3D state is something like around here. Then if you dope 20%, no, this is not gallium, germanium vacancy, and you have a P-type doping. In this case, Curie temperature dramatically. If you dope the chromium 60 or 70%, and TC goes up to the very, very high concentration. In this case, if you look at this one, you can discuss this is something like a square root behavior. Then because of we have a very large amplitude of chromium 3D state. In this case, channel double exchange mechanism becomes dominant. It depends on the concentration like this. Okay, now I would like to move to previous talk is just like a homogeneous system. Then we should discuss an inhomogeneous diluted magnetic conductor fabricated by spinodal nanodecomposition. In this case, we can design the high blocking temperature very easily. This is a case of the effective chemical pair interaction between the, for example, manganese and manganese as a function of the distance like this. This is a manganese-manganese interaction, germanium, gallium for the manganese gallium like this. This VIJ is the effective chemical pair interaction. Then you can see the calculated result. This is negative in the very attractive interaction, and this is very short range, like this. Then during the diffusion, if manganese meet with the manganese, they cannot separate. We call it fatal attraction. Then we can mapping on the Ising model. Then you can simulate the crystal growth and also spinodal nanodecomposition in this case. All of the case, very short range, very attractive interaction. So, for example, now this is a three-dimensional diffusion. We can see the clustering. If concentration is very low, like a 5% doping, in this case, you can see this is a Monte Carlo step versus TC. This is a completely you can see gradually see small clustering. So inside the cluster, you have a very strong ferromagnetic coupling, but because of the short-range exchange interaction due to the double exchange, this cluster and this cluster cannot talk to each other. So TC gradually decreases. Then finally, it becomes TC is 0. This is called superparamagnetism. But if concentration is more than 20%, in this case, you can see you have, with increasing the Monte Carlo steps, you can see that you have a completely connection in whole your crystal. Then you can see TC dramatically increases like this. Then, for example, this is a case of chromium doped gallium nitride. This is a completely disordered phase. In this case, TC is only 100 Kelvin. Because of the short-range exchange interaction, we have very few percolation paths. Because of that, TC is very low. Now, after the spinodal nano-decomposition, you can see high concentration, low concentration. This part is a pure gallium nitride. This is a chromium nitride with a Wurtzite structure. Then you can see that you have a completely percolation path for the ferromagnetic interaction. Curie temperature dramatically increases like this. So, this kind of technique is now possible. Then, for example, we can simulate the blocking temperature. For this is a disordered system. This is a three-dimensional growth. You can see this kind of quantum dot. Two-dimensional crystal growth. You can see this kind of nanowire. We call the combo phase. In this case, shape and also magnetocrystal anisotropy is this becomes this is very long, and then this becomes very large. In order to flip the magnetization, you can see the blocking temperature increases very dramatically compared with the disordered system like this. So, if in this case, system is completely superparamagnetic, not ferromagnetism, because this nanowire and another nanowire cannot talk each other ferromagnetically. So, but still you see, you can observe this kind of hysteresis because of the very high blocking temperature like this. So in many experiments, people observed small hysteresis and very low concentration region. People observed a very high blocking temperature, and especially Nate Newman, he measured a very, very careful experiment, found that this kind of nanowire, in this case, blocking temperature becomes more than 1,000 Kelvin, like this. Then now, using the 10 minutes or something like this, I would like to discuss the design of the D0 ferromagnetism. D0 ferromagnetism means, for example, you can choose like magnesium oxide or calcium oxide. This is band gap is, in the case of magnesium oxide, 7.8 electron volt. Then if you dope acceptor like a nitrogen or single acceptor nitrogen, double acceptor carbon, in this case, in the impurity, very large band gap, you can push up the impurity state, and with the increasing the concentration, you can make a partially occupied deep impurity band. In this case, based upon the Zener's double exchange mechanism, we can stabilize the ferromagnetism. In this case, if correlation energy becomes larger than the impurity band width, then you can stabilize the ferromagnetism. But we do need a partial occupation like this. Then 2004, we proposed this kind of carbon or nitrogen doped this kind of alkali metal oxide becomes a ferromagnetic. And then 2007 and 8, we have a lot of reports. One is nitrogen doped strontium oxide or nitrogen doped magnesium oxide. This from George Sawatsky's group. This from IBM Almaden. They doped very high concentration, 25 and 13% of the doping. They observed room temperature ferromagnetism. But we did a calculation. That is, you can see that if you dope the nitrogen in magnesium oxide, nitrogen acceptor level is pushed up into the band gap. Band gap is 7 point, very large band gap. Then this is partially occupied. You see very large exchange splitting. This is half metallic. Then we can calculate the exchange interaction as a function of the distance. This is very short range. Then using the Monte Carlo simulation, we can calculate the TC versus concentration. In order to go beyond the room temperature, we need more than 20% of the doping. But people observed very high TC, even very low concentration region. So I think that if system is homogeneous, we need a very high concentration of doping. 1 or 2%, it's very difficult to realize the room temperature ferromagnetism. Then after that, many people start doing experiment using the pristine MgO without any doping, but controls the magnesium and oxygen vapor pressure. People observed ferromagnetism. This is also transparent and just controls reducing the magnesium vapor pressure. You can introduce a lot of magnesium vacancy. Then people observed room temperature ferromagnetism in pristine MgO. Then we also did the calculation. You can see that this is the oxygen 2p band. It's very narrow, something like a bandwidth of 4 electron volt. Then magnesium vacancy is a double acceptor. Then you can make a whole doping. Then with a very large exchange splitting like this. Again, exchange interaction is not so very long-range exchange interaction. Then you can calculate the TC. But if you got 15% of doping, you can go beyond the room temperature, something like this. But we calculate the effective chemical pair interaction between the nitrogen and nitrogen. This is if you dope the magnesium vacancy, we can calculate the effective chemical pair interaction between the oxygen and oxygen. In this case, you can see that nitrogen case is very attractive, and magnesium vacancy case, first nearest neighbor is a little bit repulsive, and the second nearest neighbor is very attractive. So three-dimensional diffusion, you can find this kind 5% dope. You can find a small cluster. So inside the cluster, you see very strong ferromagnetic coupling, but this cluster cannot couple. And then this should be super paramagnetic, and TC is 0. But if you grow layer by layer, you can grow this kind of one. This is very long, and exchange interaction is very small, very large, but very short range. But this nitrogen stays first nearest neighbor. You have a very large magnetic moment. In order to flip the magnetic moment, you need a very high blocking temperature. In this case, you can observe the hysteresis. That's the case people reported. And for example, 1% magnesium vacancy doping, substrate temperature, room temperature, you can see this kind of hysteresis. But if you change the substrate temperature, room temperature, 350 degrees C to low temperature, like room temperature, you have a much more larger hysteresis. Means this is vacancy alignment is very important. The 4% doping, you can see that very large hysteresis at the room temperature. Now, with increasing the thickness of the thin film, you can see hysteresis becomes larger and larger from red to green to black, like this. This is transparent ferromagnetic, like this. So now you can realize that these are ferromagnetism, and we should discuss how we can use this kind of very strange super paramagnetic material for the devices. So this is a case, for example, magnesium oxide, magnesium vacancy. This you have double acceptor here. This is magnetic. Large exchange splitting for the double acceptor, and the oxygen vacancy is just in the almost mid-gap space. Then if you dope the magnesium vacancy and also oxygen vacancy, this is a double acceptor, this is a double donor. So during the crystal growth, you can dope both because of this is much more stable. Because of the oxygen vacancy, the double donor can compensate the magnesium vacancy. This is a double acceptor. You can do calculation. Then you see this state is pull down to the valence band. This is push up like this. Then this is completely compensated. Then this is very stable. And during the crystal growth, you can grow this kind of one-dimensional nanostructure. But in both cases, you have a magnesium vacancy and oxygen vacancy. So this is insulator because of the magnesium vacancy is compensated by the oxygen vacancy. To apply the electric field, oxygen vacancy migration barrier is very small. You can remove up the oxygen vacancy. Then it becomes a P-type conduction. Then people did this kind of devices, and also you can see this kind of current versus voltage. This is a hysteresis, and also people observe switching, and also people observe the ultraviolet and emission. This comes from the This comes from we have a co-doping case, this state and this state. Then from this place to here, you can observe this kind of photo emission, and in this case, like that. Then this kind of thing, we checked many kind of systems, like a nickel oxide. This is a charge transfer insulator, and ground state is antiferromagnetic. You can have nickel vacancy and oxygen vacancy at the same time. This is compensated. Then apply the electric field. The oxygen vacancy can migrate. Then it becomes P-type conductor. This is something like a mechanism of the switching. And then you can see that if oxygen vacancy migrate, it becomes conductive, and if oxygen vacancy is compensated by the magnesium vacancy, this is completely insulator. Then oxygen vacancy migration barrier is very, very small. You can easily just apply the small electric field. You can make some migration for the oxygen vacancy like this. So that's good. Then I also working for the energy creation material, like using the spinodal nano-decomposition. So if you mix the zinc oxide and the gallium nitride, band gap is almost same, and Lasch constant is almost same. Gallium nitride and zinc oxide, if you mix, you cannot mix very well. This is just like oil and water. You can see this is a spinodal line as a function of the concentration, and this is a binodal line, something like this. If you adopt more than 30%, already you can find the spinodal decomposition. In zinc oxide matrix, you have a precipitation of the gallium nitride like this. But this interface is just like a 2.7 electron volt, and then this is blue color. Then this color becomes yellow because of this mixture absorbs the blue color. Then for your eye, you can see the yellow color like this. This is called complementary color of the blue, like this. Then water splitting level is just between the here and here. Then just using this one, Professor Domen tried water splitting by visible light. But they can use only blue color. Because of the interfaces, something they cannot use red and yellow or something like this. So, but most of the interest point is if you adopt manganese in gallium nitride, that is much more interesting. You can see that a very large exchange splitting on E and T. This is E level and T2 level like this, and without any manganese doping. It is transparent because the band gap is 3.3 electron volt. If you dope manganese, it becomes this kind of color. Then absorbs the visible light. Then you can see this is optical absorption of the gallium manganese nitride. You can see 1.5 around here. This is from E state to the empty T2 state, like this. This absorption you can observe. Then if you dope the silicon donor is very just below the conduction band. This compensates this hole. Then you can don't see anything. Then this is photoconductivity. You can see that if this electron is excited from to here, then this electron jump in here. Then you have a mobile hole. Then 1.5 electron volt. We have this kind of absorption. Then 1.8 electron volt. If electron is excited from to here, this is a manganese, I think manganese 2 plus. Then this 2.1 electron volt excitation from to here. Then you have electron is moving. Then you observed also photoconductivity, and also 1.8 electron from top of the, in this case, from top of the valence band to this empty T2 state. Then holes start moving. Then you can absorb the 1.8 electron volt is a red color, 2.1 is a green, and this is infrared, and this is ultraviolet, 3 point. This is a direct band gap for downspin state. Upspin state is we have this kind of impurity state. This is magnetic because of that. Then whole visible light, you can absorb the manganese doped gallium nitride. Then water splitting level is between here and here. Then of course this is not homogeneous. You can design and also realize the spinodal nano decomposition. Matrix is a beautiful gallium nitride, and you have a manganese high concentration region like this. Then we can do water splitting using the manganese doped gallium nitride using the visible light. But another interesting point is I found that the CO2 reduction energy level is just below the gallium nitride conduction band. Then this means we can try the artificial photosynthesis. We can, using the visible light, you can excite the electron from here to here to here. Then using the CO2 reduction level, we can make from CO2 to this formatic acid or something like this. Yeah. HCOOH. Then this is we call the artificial photosynthesis. Then manganese doped gallium nitride material is a very good candidate for the artificial photosynthesis. We are now making an artificial leaf, and our leaf is always green because people use different material. But our artificial leaf should be completely black, and then we can absorb all of the visible light. Then now Panasonic companies, before they used the gallium nitride, and also you introduce a little bit aluminum, increase this band gap, something like this, increase the band gap. But they cannot use, they use only ultraviolet. They cannot use the visible light. Then now manganese doped gallium nitride are very, very I checked all of the elements, and this is the best candidate for the artificial photosynthesis so near future. You can see, for example, for example, this is band gap for the gallium nitride, and you can see that this is optical absorption like this. This part is a photoconductivity. In addition to the ultraviolet, we can use this part in order to make some artificial photosynthesis like this. I think, yeah, that's good. This is a summary of my talk. And I discussed spinodal nanotechnology. This is the new class of the bottom-up nanotechnology. Then we can make a very large scale of size. And I'm now mostly working for the photovoltaic solar cells or another energy creation materials using the spinodal nanodecomposition. And also here I discuss computational material design for semiconductor nanospintronics. I discuss magnetic mechanism and also co-doping for high TCDMS, and high solubility of the 3D transmetal is possible in the 4-6 compound semiconductor. This is a new candidate, and I should do that. Then spinodal nanodecomposition is possible using the comb phase and the Dirac phase. We can design the very high blocking temperature. And also I discuss water splitting, gallium nitride and zinc oxide mixture. In this case, we can find the spinodal nano decomposition, and also water splitting and photosynthesis by visible light is possible using the manganese doped gallium nitride. Okay, thank you very much for your attention. That's the end of my talk.